2 days. Stay here. I always forget, I can't look at my stuff if I'm sharing my screen. I have to be more careful. Cool, so it seems like we have a pretty good idea that we need to warn the astronauts that in 2 days, they need to stay inside, batten down the hatches on the ISS, and make sure they aren't dealing with being out in space while they also get hit by an intense dose of charged particles from the sun, from the CME. So I have one more challenge question. Anyone can guess. This is a little extra, so if you feel like you have an idea, shout it out. But in the activity, I mean, the astronauts were actually never in danger, not just because this happened in 2002 and we're doing it in 2020, but also because for another reason. So I'm wondering if anyone has an idea, why would this coronal mass ejection not actually be a problem here on Earth or in low Earth orbit?
It seems like the intensity and like how concentrated the particles are is dissipating over time.
So that's part. We're still going to have a pretty extreme burst. I guess maybe if the moon was in the way, so that's not what's happening. It could help, but that's not what's happening here. So I want to remind you that these images of the sun were taken from Earth. So we're looking at the sun from Earth and we're imaging this coronal mass ejection. What do you notice? How is it? Is it? There we go. It's not coming towards us. So we got this in the chat. It's not actually moving towards us. We can observe it really nicely because it's shooting out in a different direction. So if there was one that was coming towards us, we would have to do some different measurements to actually get this. But it's a little bit more tricky to actually see when they're coming towards us. So we looked at one that was not actually moving towards us. So that's my little trick question there. But still, the astronauts are safe. Y'all did it. Cool. Sorry, I'm kind of a nerd with all of this, but so just a last few things before we move inside the sun as we wrap up today. Kind of on a similar note, so we can see the coronal mass ejection was an ejection of charged particles. We can also see solar flares, which are intense bursts of radiation. So radiation is going to be photons instead of particles, instead of electrons and protons, and those like the coronal mass ejection, radiation in the form of photons. But these also release a huge amount of energy, similar to about 1 billion megatons of TNT, and we just see bright spots on the surface of the sun. Again, they're related to where the magnetic fields are coming off of the sun. So we often see them between sunspots. As I said, the coronal mass ejection was a form of solar wind, but this is just a stream of energetic particles. So protons, positively charged particles, electrons, negatively charged particles, as well as something called alpha particles, which are 2 protons stuck together. It's what's left over in a helium atom after it gets stripped of electrons. So helium, protons and electrons, hydrogen. And this is just material that's being ejected from the corona, and they travel very, very fast, so up to about 1 million miles per hour. One thing that was sort of cool I wanted to share with you all is that a recent NASA mission is the Parker Solar Probe. So this might also be a cool thing to look into for a project. I can also shoot out information about this. But one of the things the Parker Solar Probe is doing is actually listening to the sound of the sun in the form of solar wind. So what you're hearing there are measurements from the Parker Solar Probe of how it's measuring the intensity of the solar wind over time, which I just think is really cool. So this is a recent mission that's being shot towards the sun, and it's measuring a lot of So that's some of what, if you were approaching the sun, what you would hear as you moved through the atmosphere and through this charged particle stream. So the sun is actually pretty noisy, but we're learning a lot more. We're still trying to figure out this solar wind, but the Parker Solar Probe is giving us a lot of new information, which is super exciting. So that's the exterior of the sun. Now we're going to start looking inside and specifically at how the sun creates energy that actually gets radiated down and lets us feel nice warm sunlight. It's a beautiful day out here in Walla Walla, so you can go outside and get tan or wear sunscreen and be safe, I guess I should say. But we feel the radiation here because of what's happening in deep inside the core of the sun. So we're gonna talk about that a little bit today and then hopefully wrap that up on Thursday. I just wanted to also give a quick plug for the Sun Lab, which is one of the options for labs we can do. Right now, it's one of the ones that's open. It's also the only one open that you can do from the comfort of your own home. It completely doesn't require any app download. It's all either on a computer or in your brain. But it's a fun one where you can really explore a lot of what we've talked about with the sun. But one of the things you do in this, and I just wanted to point out, is that you look at the spectra of the sun. So this is what we kind of talked about when we looked at measuring light. You can pass light through a prism and spread out that light as a function of color. So that's what these folks have done with the sunlight. We can see light as a function of color from the sun down here. And they've also plotted it versus intensity. So this is how bright all of the different colors are, or how bright the different wavelengths are. So looking at the sun spectrum, we can use Wien's law to find the peak of the sun spectrum, and that'll tell us the temperature of the solar surface. And we can also use these absorption features, these dips, to figure out what elements are present in the sun's surface. So just like hydrogen could only absorb and emit certain lights, certain colors, certain very specific wavelengths of light, the elements in the sun's surface can only absorb really specific types of light, really specific energies and wavelengths. And we can use these dips to estimate what's there. So for example, this big dip right here in the red is hydrogen alpha. So that tells us there's hydrogen here. There must be hydrogen in the sun because of this dip here. So if you want to play around with this on your own, I highly suggest you check out the Sun Lab. I like it. It's a bit longer, but the last part focuses on this. So if you want to earn 7 lab points, it's a great one to check out on your assignments page. Now moving in from the surface, slightly old. So on Tuesday last week and today, we've talked about the outer layers of the sun's atmosphere. Now we're going to dive inside. This is just a reminder to point out nothing here. We have observed nothing of this. None of this has been actually, we have not sent anything inside of the sun. All of this information that we are going to work through, we find out by doing detailed measurements of the sun's surface, measuring the amount of energy coming off of the sun, and then using physics to figure out what must be happening inside for us to see the amount of energy we do come out of the sun. So for the sun to be producing the amount of light it does, there are only certain ways it could do that, and we can figure that out using what we know about energy production here on Earth. So just kind of a fun little fact, the sun actually emits enough energy. If we could gather all of the energy being emitted by the sun in 1 second, if we could gather all of that energy, it would power the entire United States for 13 billion years. Unfortunately, out here at Earth, we're only getting a very small fraction of that energy, but it still is a good plug for solar energy in the future. The sun is putting out a ton of energy, and if we can harness that, we can have an option besides coal to burn. So first of all, I want to talk about what the sun is actually made of. So in order to think about what it would be like if you were inside of the sun, besides very, 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 very hot, we need to start considering a new phase of matter, and that is plasma. So the sun isn't a solid, it's not a liquid, it's not a gas, it's actually a plasma. The sun is completely made up of plasma. And so what that means is that a solid is something like ice, like a table, like a book, anything solid. We interact with these a lot, and it's just the atoms are lower energy, and they're all kind of held together through electromagnetic forces. As you increase the temperature, those atoms can start wiggling a bit more, and we get a liquid phase, so like water, tea, beverage of choice, liquid mercury. But those are going to be higher energy. We get things that can fill containers, and that's our kind of liquid. We're used to that. And then gas, again, like the air, what we breathe, if you increase the temperature more, steam in terms of water, the particles start bouncing around more, they move faster, and we get a gas. The fourth matter state is then a plasma, and that's when you've heated things up so much that most of your elements inside of this material are going to be ionized. So instead of nice atoms, we have protons and electrons. So you might have some atoms that haven't lost all of their electrons, but a lot of them have. So instead of having atoms that are neutral, so an equal number of protons and electrons, you have ions, which are the positively charged parts, and electrons, which are the free electrons, which are the negatively charged parts. So in a plasma, things are so hot that the atoms can no longer hold on to all of their electrons, and a lot of them get bumped off and start flying around, and we get free electrons and ions. So this is just charged materials. It's the highest energy form of matter, and pretty much all of the sun is hot enough that we're only going to get a plasma inside of the sun. So a few other places where you might have experienced plasmas. If you've ever played with one of those plasma globes, I don't have one here, I should, that'd be fun. That's actually the material inside of that is a plasma. So instead of being heated to extreme temperatures, there's electric currents running through those globes that cause the gas inside to ionize and become a plasma. Neon lights, any kind of lights like that, though, and incandescent bulbs, I think, are plasmas inside. So those, again, streams of electrons through electric circuits, sort of. So when you turn on a light, one of these kinds of lights, the gas gets excited by electric currents. So that's another way to create a plasma instead of just heating it up. And then also lightning bolts are going to be plasmas that we can see here on Earth. So we get charged particles bumping around in the clouds as water ices bump into each other, and those discharge in the form of a plasma, a stream of charged particles that is coming down to the ground to go to a neutral source like the Earth or tree or whatever else it can reach, which is why you do not want to be outside during a lightning storm. So that's kind of where you might have seen plasma. It's just the highest energy form of matter, where instead of nice neutral atoms, we're getting positively charged ions and free electrons. Since everything is bumping into each other so much, we can bump those electrons off and they run out and do their own thing. They don't do their own thing. They're still in the plasma together, sorry. They're just not held together in the atom. besides being a plasma, our sun is mostly made out of hydrogen. So the smallest element on the periodic table, one proton, one electron, um, it's 90% of the atoms in the sun are going to be hydrogen. But because hydrogens are so light, because they're just one proton, one electron, they're only about 70% of the mass. So 90% of the number of atoms, 70% of the total mass. Most of the rest of the sun is going to be helium. So the next smallest element, two protons, two electrons. But because it's two protons, it's about twice the mass of hydrogen. So actually it's 4 times because there's also 2 neutrons. Sorry, I forgot. So high helium is 2 protons, 2 neutrons, 2 electrons. So it's much more of the mass of the sun. Almost 30% of the mass of the sun is going to be in helium. And then besides hydrogen and helium, there's also smaller amounts of oxygen, carbon, nitrogen, silicon, magnesium, and iron. So we can tell again by looking at the spectra of our sun, looking at these dips, and figuring out what energy of light corresponds to specific elements. And we can determine the composition of the sun with the spectra, looking to match these dips with the specific elements that will produce or absorb light at these wavelengths, at these specific energies. Any questions there, actually, before about plasmas or how we determine the composition of the sun? So beneath the surface of the sun, we have our first layer, and this is probably where we'll end about since we got 4 minutes left, which is the convective zone. So this is where energy is transported through convection. So convection, just really quickly, is when warm materials, like boiling water, warm materials rise. As they rise, they cool. As they cool, they fall. So here, we're seeing a mug of hot water is being placed under water with some food coloring. So we can watch the food coloring as it heats up above this hot mug. It starts to rise. And then it also pulls up material, even cooler material near that. The important thing is the hot material is rising. As it reaches the top, as it moves away from the warm source, which in the sun is the core, in this example, it's the warm mug. It starts to cool. As it starts to cool, it wants to fall again. So we're getting hot material rising, cooling as it gets away from the warm source, and then falling as it gets cold enough. As it's cold enough, it falls, and then it gets pulled back, heated up, and rises again. So convection is just this, this boiling motion, warm material rising, cool material falling, and getting nice cycles of this throughout time. So this is same thing if you boil water to make ramen or hot chocolate or whatever else, this is what's happening in your water. It's also what's happening in about 70% of the sun, how energy is transported in about 70% of the sun. So the base layer, the bottom of this layer, the part in the interior is at a temperature of about 2 million Celsius, and then there's the convection layer extends to the photosphere, to the surface of the sun, where the temperature is about 6,000 degrees Celsius. So there's a huge cool down in this 7.7 solar radii, 70% of the sun. And in that space, all of the energy is being transported through convective currents. So we're bringing heat energy from the center of the sun out to the surface through processes of convection. In this level, it's cool enough that some of those heavier elements will be holding on to their electrons. So we're still in a plasma. There's a lot of free electrons and charged ions, but the carbon, oxygen, those heavier elements won't be completely ionized. So that means they've lost some of their electrons, but oxygen has 8 electrons. So maybe it's lost 4, but it's holding on to the other 4. So we'll have 4 electrons and a +4 oxygen. so an oxygen with a +4 charge. Because of this, because there's so many free electrons and also positive atoms, photons cannot stream through these. They'll start bumping into stuff and they won't transfer energy nicely out of the sun in this layer. So there's two ways you can transfer energy in the sun. You can do it through convection or you can do it through radiation. In most of the sun, we're transferring energy through convection. The other way we know this is because at the surface we saw those boiling granules. So last class we looked at the images of the surface where you could see it looked like it was almost boiling, which means that it's a convective surface. So we can see the blobs, the hotter blobs where warm material is being brought up, and the darker tracks where the material is starting to fall down. So that's another way why we know that there's convection happening inside of the sun. So that's the convective layer. Next class, we'll get into the radiative layer and we'll look at how energy is actually being produced in the core. It is 12:50 though now, so class is over. There is lab tonight. If you want to do that sun lab, I'll be hanging out on that Zoom link. And so maybe I'll see some of you there, or on Thursday when we talk about energy production in the sun.
Thank you.
Thank you.
Thank you.